participants, good afternoon. We were waiting for you today. And we have, this is now, I think, 7th day, including one quiz day. I came to know that many of you have not been able to submit. My request to you all is to please attempt once. You are given extra time. And if you need further extra time, please feel free in telling the professor. So we expect you to please attempt some questions from the question paper. Thank you. With this, I request Professor Bengt to please continue with his lecture.
Okay, thanks.
Thank you, Professor. Yeah.
So let's share my screen. And yeah, based on the small feedback I got from the small exam, I realized that it's probably a bit tough for you, so you need more time to solve this. And yeah, I mean, this depends totally on the background, and if this is new material, of course, it needs some more studies to understand it. So what I will do today is that I will soon go on with temporal logic and a specific calculus around that called Mule calculus. It's a general calculus for generating or computing fixed points. So it can be useful in actually not only for this purpose, but more generally, it's a fixed point formalism, which is quite common for many algorithms in computer science. But before I start with that, I would like to sum up and also further generalize the modeling tools related to Petri nets and to automata with variables. So actually what I will present now is a complete, you could say, state variable oriented model, which means that I assume that I have a set of variables and altogether they generate the state of the system. Like in control, for instance, you have state space models, and they constitute together the state of the system. And if you remember, the Petri net had a marking vector, and the marking variable for each place then represents, yeah, all the markings together then could represent the state of a Petri net. So for instance, if you have 10 places, you introduce 10 variables, and in that case you have also 10 variables in your state vector. For that, you can define transition relations, and actually what I call then a predicate on the transitions, and also predicate defining the initial state or possible initial values of X. It could be one unique value of the state vector, but it could also be a set of different values of the state vector that are possible initial states. And in the same way, you can also decide goal states, either as one unique state or as a set of states, depending on how you formulate your predicate. And this type of model I proposed like 10 years ago, and you could say that it's not very unique. Others have done similar work, but maybe not exactly this. But you could also say that it's an extremely general model. So in that sense, more or less everything can be captured in this way. So what I was doing with this model then in the beginning was to promote that, well, okay, an automaton, a Petri net, an extended finite state machine, an automata with variables can all be described in the same way by this framework, modeling framework. But from a practical, yeah, okay, and that is actually quite nice from a computational point of view, because what I formulate here is, as I have said a couple of times before, perfect for computational algorithm. But to make this a bit more user-oriented, you could say that Petri nets with or modular Petri nets, where you also take the freedom to add variables for to represent the more logical behavior of the Petri nets, for instance, mutual exclusion, etc. That is what I call then Petri nets with shared variables. That is my favorite model for myself, and that is maybe the main contribution of my work earlier then. So I showed you this model, the automaton and the Petri net, and both of them can be described by this type of predicates. So the predicate down here, the first one says that, okay, when the event A happens, and if there is less than 4 elements in the buffer, you can add one more element. And you can remove one element if the current value is greater than 0, and if the event B is happening. So this was something I showed you in the start of the course. And now I just repeat this and show how this can be used for instance, Petri nets with shared variables. So then one interesting thing is that the synchronous composition can also be defined for this type of models in a very, I would say, elegant way. So you just take the AND operator between the initial predicates and the marked predicates. You take the union of the events as in the ordinary synchronous composition, and then we assume a global set of state variables that are valid for all systems. So that means that the set of states or the set of variables is the same for both G1 and G2 here. And then the predicates or the transitions are described by a predicate defining the current value and the next value. So this was an example of a predicate describing what is valid now and what can happen in the next update, so to say. And here we can separate between the event and the rest of the guards and actions in this formula. And in this way, we can take the conjunction between the individual predicates for the transitions. And so this gives you a very compact description. Not very readable, but once again, very useful for computation. Now I will show you how this can be done, can be used for Petri nets. And here you see just with 3 sequences of tasks, it's actually already here quite a number of arcs going back and forth, just describing the logics around these 2 resources, R1 and R2, and the fact that the event C1 must happen before you can execute C3 in this case. So then the question, would it be possible to make something where these resources R1, R2, and P are more described by logical variables, or not logical, integer variables? And the answer is yes. Then I also introduced a shortcut. I did that also last time, saying that, okay, R plus means that the next value is equal to current plus 1. And RK minus means that the next value is RK minus 1. And in this case, I use this for the 2 resources R1 and R2 here. I haven't defined exactly the domain of the variables here, but that's of course a flexible thing. Say in our example here, we assume that R1 and R2 has the domain 3 from the beginning, and yeah, the question is which domain you have on P, but it should at least be a limited number of elements that are possible for different values of P. So in this case, R minus means that we require a token from R1. We take that and reduce the value, saying that, okay, now there are only one less, there is one less free R1 token, because one of them is consumed by this A1 transition. And then here at C1, we give it back. So then we add the number of free R1 resources. And P plus here means that you increase the value of the variable P, and in C3, then you reduce it. And then the C3 variable or C3 condition or action can only be executed when there is at least one element in the P place, or that P is greater than 0, because then you can reduce it one step and it still works fine. So I would say that this means that we book R1, this means that we book R2, this means that we release R1 and R2, and here we have the opposite, that we book first R2 and then R1, and then we release R2 and then R1, etc. So I argue that this is easier to understand and to read. You, as I used to express it, you use the pictonet for what it is good for, namely to describe the flow of tokens in the system, the sequential flow of tokens, while the logics, the restrictions of the transitions, is better to describe by logical variables instead. So if we look then at the first sequence, the first local pictonet, because I mean, note here that now we have 3 pitronets that are going to be shared. And you see there are no shared events. The communication between these 3 pitronets is only performed by these shared resources or shared tokens between the first and the second for R1, the first and the second, and even the third for R2. So in this case, we have, for this local pitronet, we have 4, no, we have even 5 marking variables, one for the first place, one for the second, third, fourth, and fifth. And the fifth is M15. And 1 here means the first pitronet, the first, the left pitronet. Just to describe how these transition conditions could look like, we take a specific look at this A1 transition. And that looks like following. To be able to perform A1, we must have at least 1 token in the input place. And that means that we also reduce, when we perform A1, we reduce the number of tokens in this place with 1. And we add 1 token to the second place. At the same time, we reduce R1 to R1 minus 1. If that is possible, based on the domain of the variables. If this is possible, then when the execution of A1 occurs, then this will be updated, and that means specifically that the next value of M1 will be the current -1, and for M2 it's the opposite, that you add one element, and for R2 it's also that you take away one element. The complete transition predicate, what is that? Well, here I want to emphasize that it's not all variables that are updated. In fact, this predicate only have an update on M1, M2, and R1. So the rest should then keep their current value. And that means that we need to also specify that. But that is something that it's just a machinery, but it's necessary to add that. So that means that the third, fourth, fifth M variable and R2 and P, they keep their current value. So next M3 is equal to current M3, M4 the same, and finally P, next P is equal to the current P. So this is now a complete transition predicate that can be used to formulate a complete model, and based on this predicate you can also simulate the system and so on. So this is an equivalent formulation compared to, for instance, the transition matrices with the input and output matrices A plus and A minus we had for the Petri-net. So with this, I will stop and finalize the presentation of these extended models. But before I complete it totally, I will also show you two examples how this could look like. So the first is from a current exam, where I just give a set of predicates here. So consider the following predicates. And based on that, I try to explain where the variable E can take values 0, means nothing, or the events A, B, C, or D. And that means that only one of either E is equal 0, or A, or B, or C, or D. But it's equal 0 when no event occurs. The prime symbol is used for the next value of a variable. And the initial value is that X is equal 0, Y is equal 3, and Z is equal 0. So based on this, we are asked to formulate a Petri-net that represents this predicate. We can just take a look at the first part here at least. Then we see that X prime adds one element, it's equal to current plus 1, while Y is updated such that Y is reduced one step. And this happens also when the event A occurs. So then we can look at the Petri-net and see that, okay, this represents this A transition, because E is equal A. And then we have another transition predicate for B, C, and D. And if you evaluate these in more detail, you get this type of Petri-net model with two flows, simple ones, and one shared, say, resource or something that can be used by both tasks. And the initial value of this is 3, meaning that, for instance, you have 3 resources of this type Y. So B here then generates a corresponding reachability graph for this, and let's see what it said. we should model the updates of these variables. Then we have, that should be, let's see, sorry. I should done it like this. Generate an automaton that models the same behavior as the predicate or as this Petri-net. So for instance, when A is happening, you add one element to X, and the states here are not they are the X value of X and Z. So in this case, with an A event, X is increased to 1, while Z is the same, 0 as before. And then we see that one more 3 A's in a sequence generate 3 tokens in the first place, but then you cannot add any more. You have to do at least one B event to get something back here, so you can continue and also execute C and D events. So all the possible states are given by this. And then the question is also, let's see here. What type of system does this predicate represent? Yeah, I mean, it's 2 tasks that have a shared resource with capacity 3. So, of course, we can say that, I mean, this is not very readable, while this Petri-net model is for sure something that could easily be understood, but you could also divide it into 2 nodes and use this y plus and y minus to represent this this resource. For instance, here we should have a y minus and here a y plus. Here also a y minus and a y plus to model the behavior. In the next example here, I ask for the opposite, namely to generate a predicate description for this Petri-net with its resource variable R and the number of tokens in the places M1 and M2. And here was the original model, and here are some updates of both M and R. And you see it generates the similar type of logical equations as we have seen before. And for in case, sorry, in example, in the part C here, we ask for the synchronous composition of the automata for representing these variables. So we have one automaton for M1 and another for M2, and the third for the R variable. And then we also ask which kind of invariant condition we have here. So we can say that any type, this is an interesting remark, that any place in a Petri-net can, in an automata, with an automata, be described as a buffer in the same way as I showed you earlier here in this example. This is a bounded Petri-net, and this type of system can always be described as this type of buffer model. And this means also that any place in a Petri-net can be described in the same way. So this is exactly what we see here, that these variables can also be represented by buffer models. And if you generate the synchronous composition, you get this. And then the question, what kind of properties do we have for the combination of the variables M1 plus M2 plus R? and the invariant condition is that the sum is equal 4. Either you have 4 elements in the resource R, or they are distributed in the place M1 and in the place M2. But the sum of M1, M2, and R is always the same, namely 4. So by this, I would like to go on with temporal logic. And temporal logic is of course a logic that describes the behavior of a system where we to compare with propositional and predicate logic also introduce some temporal properties. But it has its basic in what is called modal logic. Maybe you have heard about that in some courses on basic logics and philosophy and so on. In modal logic, there is one additional aspect that there are 2 basic so-called modalities. And that means that a statement P includes the possibility to say, well, it's absolutely sure that P is true, or it is possible that P is true, but yeah, there are some kind of uncertainty around this. So P is possibly true, P might be true, P is usually true, are synonymous notions for this more vague statement. And then it's interesting that when you put the negation on these statements, they are complementary to each other. So, for instance, if you say it's not necessarily true that P is true, that means that it is possible that P is not true. It's possible that P is not true. That is the same as to say it's not necessarily true that P is true. So if we write possibly P as this diamond and necessarily P as the square, this statement above here, it's not necessarily true that P is true. If you say that necessarily P is true, then you write square P. And then if you take the negation of that, that was what I described here. It's not necessarily true that P is true. That is what is said in the first sentence. But that is equivalent to say, it is possible that, and possible is written by the diamond, that P is not true. And then you put the negation in front of the atomic proposition P. So not square P is equivalent to diamond not P. So when you move the negation inside this expression, you have to change the necessarily to possibly. And that means that you can also define actually necessarily P as not possibly not P, and possibly P can also be expressed as not necessarily not P, which when you say that not necessarily not P, it is the same as to P, say that, yeah, okay, P is possible. So that was modal logic, and temporal logic is just an application of this modal logic that was introduced some, well, long time, I think it was like 40 years ago or something. And it was specifically a professor from Israel, Pneuli, who introduced this temporal logic into computer science. And then we can say that this necessarily is then replaced with always, and possibly it's replaced by eventually. So that means that, okay, if I introduce two basic atomic statements or propositions, the heater is on and it is warm. Okay, if the heater is on, is it absolutely true that it's warm? No, because when you just switch on the heater, it's not warm in the room, for instance. But we can say that it's always as follows, that P conditional eventually Q, meaning always, if heater is on, eventually it will be warm. And this is a more expressive and true condition, that, okay, if a heater is on, it will eventually, we don't say exactly how long time it will take. So this is not a quantitative expression, it's more a qualitative expression, saying that, okay, in some time, finally, eventually, it will be warm. So these two operators, always and eventually, they are the main contribution into two specific temporal logic systems or languages. One is called linear temporal logic, and the other one is called computational tree logic, CTL and LTL. So we start with the linear temporal logic. And then the question is linear time. What does that mean? And it's interesting that this notion linear, for me, that is related to a linear or non-linear function, for instance, which, I mean, a function 2x plus, yeah, okay, just 2x. A function f of x is equal to 2x. That is a linear function. The output increases linearly with x, while if I write the function as 2 multiplied by x square, then it's a non-linear function. So this was what I knew about a linear and in that case the opposite non-linear function. But linear time, what does that mean? Well, I realized that also in ordinary language now it's quite common that for instance, some people say that, okay, I'm looking at linear television. That means that you are looking at the ordinary TV programs given by the television channels. While if you go for internet and you can look at the program at any time, like pods and so on, then we don't talk about linear television anymore. So linear time means formally that it's something, let me just read here. Time can be represented as a tuple where T is a set of time instances. Then time is linear if for all elements in T, we have that either Tk is greater than TL or the opposite, that TL what did I say correctly now? Tk is less than TL, or TL is less than Tk. So there is an order between the different time instances. So for instance, a linear time means that I can say that, okay, T0 is less than T1, which is less than T2 and less than T3. Things are happening in a sequential order. That is linear time. And okay, I mean, then we could say that what the usual feeling of time is that it is linear, nothing else. So then it's interesting that people can start to talk about branching time, which I will soon come back to. But that means something different, where this property of the relation between two time instances is not that simple, that every time either the first is less than the second or the second is less than the first one. So that was, you know, at least I'm interested in these names and to understand that. I mean, I asked myself for quite a long time, why do they call it linear temporal logic? But now I understand why, because they refer to this definition of linear, that is a given order between the time instances here. So linear temporal logic, LTL, which it's also called, is what we are going to define now. So basic LTL does not include explicit time instances, only linear ordering between them. So that means that the time we just describe as a number of integers, 0, 1, 2, etc. And it does not mean that we have a specific time scale with, say, one update every second or every minute or so. It just means that, okay, the time instance 1 is higher than the time instance 0, and 2 is higher than 1. But the time difference between two time instances could in practice be very different. Actually, I have no clue about that. It's just that something happens before or after something else. On the other hand, it is possible to extend, for instance, LTL with specific time instances. Like then we have said, okay, that the first time instance is 0, the second one is 2.5, the third one is 5, and then comes 10 and 17. And then these time instances are exactly, say, 2.5 seconds, 5 seconds, 10 seconds, or some other unit. So, and in that case, there are, for instance, one logic called signal temporal logic, STL, and there are also other similar logics. And you could even have timed LTL, and you could have timed CTL, as I come with soon here. But let's stay with the basic linear temporal logic, where the specific time when things happen is not defined. It's only the order between time instances. Then we have a couple of basic LTL operators. The first one is the next operator. So that means that at the next time instance, something will be true. And then I write that by a circle. There is also a letter version of these operators where, for instance, the next means is expressed with the variable x, X in next, while always, let's see here now, F is finally or eventually, and G is globally, which then is written with a G, and then there are two other aspects of this, which comes not here, but when we come to CTL, and that is A for always, and okay, sorry, I mixed these shortcuts. I think I will come back to this in another slide. But yeah, E is there exist. So there are two quantifiers, always or there exist, A and E. And for me, it's a bit confusing that always P, which you see here, it's written as a square P, that can also be written as globally P with the letter expressions, GP. And for me, it's more native to say always P, but okay, you can of course also say globally P. So because of the mix between and the different problem to relate the quantifier A always with the modality G globally, I go for this these notions, square and diamond and then circle for next. Okay, so first the next operator, the circle, and eventually P is the diamond modality. P happens sometime in the future, at least one time. It's actually enough that it happens one time that P is true. While always P, square P, means that P is always true. And then we have the fourth one, and that is that P is true until Q is true. And that means that P is true at all time instances until Q is true at least at one time instance, to be very careful. So now these page references here are reference to the lecture notes you also have. And here you see some examples of these linear sequences in what we mean by P, next P, eventually P, always P, etc. And here you see that, okay, P must be true in the first instance if I write P. P must be true in the second instance in this sequence. And for eventually, it must be true at least sometime in the future. What is happening in the other, at the other time instance, I don't care about. So that means that if something is true always in all states, always P, that implies actually all these others. Always P implies eventually P, next P, and P. So these circles means that anything can be true there. The P until Q was simply a number of P and then a Q, and after that you don't care. And for the eventually P, if you get one P, you don't care what happens after that. Then we have two interesting combinations of square and diamond. First, always eventually P. What does that mean? Well, actually, it means that infinitely often or repetitively, we will get a P. Okay, here we got the P, and then here not necessarily P, and then P comes back from time to time. We repeat P, or infinitely often you get a P, but it's not necessary that P is true at all time instances. The opposite order, eventually always P. Yeah, I mean, to me that sounds much more easy to understand. Okay, after some time instances, then you have always P. That means that P must be true for every time instance. Empty circle means don't care. Any statement on P and Q are accepted. Then we have a syntax of LTL. And in that case, we also include some basic propositional logic operators. So we can inductively define a grammar where we start with an atomic proposition equal phi, and then you can take the negation of that, or you can take the conjunction of two LTL expressions. And then you also have the next operator, and you have the until operator. In this grammar, we don't define explicitly eventually and always, because they can be expressed as what we call derived operator. Just to describe what we mean by this grammar or this inductive definition, I illustrate here that, okay, let's assume that phi 1 is equal P and phi 2 is equal Q, and they both belong to AP. They are atomic propositions. Then we see that by the rule, this rule with phi 1 equal P1 and phi 2 equal Q, you also generate phi equal phi 1 conjunction with phi 2 equal to P and Q. Then you can take the next of phi, and you get this next of P and Q, and you can take the negation of P and Q and actually use De Morgan's rule to get not P or not Q. And you can also write, say, phi 1 until, or phi 1 until phi 2 corresponding to or equal to, in this example, P until Q. Then we have the derived operators. And first, we have the disjunction, the or condition, which is simply not phi 1 and not phi 2. And the implication of the conditional operator means not phi 1 or phi 2. And then eventually is that just that you say true, meaning that you have no restrictions at all, anything is valid, until you get phi for at least one time instance. That is eventually phi. And then we can use this relation between the two modalities, not, or say that always P is equal to not, eventually not P. Which was exactly what was written here. And then we can also define true as phi or not phi, and the negation of true is false, or the negation of a tautology is a contradiction, and that is defined as not true. And then we had this infinitely often and eventually always phi. There are also some interesting precedence order for instance, that if I write P conditional something, that in that case, this modal operator has higher priority than the conditional operator, as well as until has higher priority and then and. And in this case, square P and Q does not mean square of P and Q. The modality only works on the single element P. To get it to work on both, you have to put the parentheses around. Now I would like to illustrate how an LTL formula can be, or LTL formulas can be used to specify properties on a very simple software program in this case. Just to illustrate that this type of temporal logic is useful to specify general software. But of course, in the illustration of this, we take some very simple aspects, and in this case, it's just that we change the value of a variable, and we try to reason about that. So this program is, while true, it's an infinite loop here. Do if y is greater than 0, then you update the y value. So you decrease it one step. So this was noted as y minus when I had this Petri nets with shared variables. So next value is y minus 1. But when y is, this was when y was greater than 0, but when y becomes equal 0, then you reset it to equal n. And then you loop around this. So what is done here, that when the variable becomes n, it steps down to 0 and then go back to n and repeat this in an infinite loop. So we can assume here that the initial value is y is equal m. That means that when y is equal k, we also call it y index k. So y is equal k is expressed as yk. So it's just a shortcut or sugar notation. So then with in a state sequence here, we can look at what happens with the variable yn minus 1 until y1, and then instead of being y0, but when the value is 0, then it's reset up to yn. Now we see that the value of y will always be in between 0 and n. So, okay, we could say that, well, we have tried to written a program where we want y to have this specification, and then you could ask, is this specification satisfied? Of course, when you have a much more complex program, it could be of interest to ask as a safety condition, for instance, is it really true that y is always in between 0 and n? And this can then be specified by the LTL as always square y0 or y1 or up till yn. But it could also be written as always the following interval, that y is in the interval from 0 to n. This is a safety specification, which is quite easy to see that, yes, okay, this must always be true. Now to something a little bit more interesting. Okay, the LTL formula always eventually y0 also holds, since y is equal 0 will be repeated an infinite number of times. It goes down to 0 and then back to value n and then back to 0 again. So that means that from time to time y is equal 0 is happening, and that means that it's repeated infinitely often, and always eventually is y0 is then true. Now another thing can also be evaluated. If we introduce the Boolean function even on the variable y, we ask ourselves, is it always that even y means that in 2 steps, next, y will also be even? Yeah, spontaneously that looks reasonable, but could we really be sure about that? Well, actually, it's not valid when n is even. But for odd n, it's true. Let's just test for n equal 2. Then you have 2, 1, 0, and then up to 2, and then again 1 and 0. And then you see that every second time you have an odd and an even number. But if you take n equal 3, you see that you go from an odd to even to an odd, even, but yeah, okay. Then the question was in 2 steps. It's valid for odd n, but not when n is even. Oh, something is strange here. Okay, it's rather when, yes, here we have a problem that, okay, here if I make two step forward, then I go from an odd to an even number, from 1 odd to an even 2, for 0 even to an odd in 2 steps. So that means that, okay, as I said here, for n equal 2, this statement is not true, while it's true for n equal 3. And then it's also quite easy to realize that for all odd sequences, for all odd values of n, this is true, but not when n is even. Okay, I mean, this looks a little bit academic and more mathematical, but I mean, the only thing we can reason here about is these values of the variable y. But I mean, it could also be that you want to guarantee, for instance, that the variable y is limited in some sense when you have a much more complicated software, and that can be done by this type of specifications then. So now we have gone for a little bit, yeah, okay, we didn't start exactly at time. Let me see if I should. Yeah, I could at least present this computational tree logic also before we take a break. So, computational tree logic what is that? Well, that is another version of logic, which was developed by some Americans, if I've got the story correct. Clark, for instance, one of the real pioneers in model checking. Maybe you remember that I recommended a handbook of model checking last week, and Clark was one of the editors of that handbook. And he formulated this computational tree logic, and based on that has developed a lot of interesting results around that. In some sense, computational tree logic is more limited, but you cannot say that CTL is a special case of LTL and the opposite. They are complementary. But the interesting thing is that these two languages can be unified in something called CTL star. But let me come back to that. Okay, for automata, including alternative sequences, an LTL formula holds if it's true for all sequences. So, for instance, we can take a look here and see that, I mean, this could be a part of an automaton. And if you go to the different states here in the automaton, and if you find, for instance, here, that, well, here it's valid in every sequence, every part of the tree here, that you have always phi. And in this case, when you start the initial state, you find that, okay, in every trace you go down here, you see that eventually you get the phi. Here, already after the first step, here after two steps, you get the phi. While in this case, it's only exists one trace, or let's see how I express it here. For all, I use the word sequences here. Okay. So here I have one sequence where phi, eventually phi is true. So that means that there exists a sequence where eventually phi is true. While here, for all sequences, eventually phi is true. Here, there exists one sequence where phi is always true. As I assume here that if I continue here, phi, at least in one of these alternatives, will be true and repeat it further. So if you take one sequence and phi is always true, then you have that there exists one sequence, at least one sequence, such that you have always phi. And here we had the fact that if you take all sequences, you always have phi. So computational tree logic can reason about the basic logics eventually and always phi, but it can also distinguish between in an automaton and in the computational tree, if this is valid for at least one sequence, or if it's valid for all sequences. And that means that CTL is actually very natural and useful for automata. Still, I would say that LTL is, in my feeling, the most popular language. Maybe because it's a little bit more general. Because in CTL, you cannot express things like this. always, eventually, or eventually always, these combined properties, they cannot be described in CTL. You could say that before every operator, that it must be a quantifier in CTL, either exist or always, or for all. That's important. Not always, but for all. So if I write, for instance, for all square, there exists eventually a P. That is a CTL expression. But to skip the quantifier between these two, which actually has quite a strong meaning, that is something you cannot express in CTL. You must always have a quantifier before each modality in CTL. So after this now comes some examples and reasoning a bit, and typical actually specifications on liveness, fairness, and so on. But we take that after the break. So now we take, say, 10 minutes break. So then,
yeah. So it is 4:10 exactly here, and so 4:20. 4:20.
4:20. Yeah.
And meanwhile, if you have any questions,
yeah,
please feel free in asking and writing in the chat box. When Professor Bengt is here, he will be responding. Okay.
Mm-hmm.
Thank you, Professor.
Yeah.
So participants, my request is that if you are finding that there's something which you are not able to understand, you're finding it hard or difficult, please feel free in telling us to Professor Bengt, so that, the basic purpose of holding these programs is to help you learn something new and develop expertise in these areas. So if you feel that, and you must have taken registration, you must have registered in these courses because of this only. So my request to all of you is to please feel free in asking anything that you feel that is not clear to you, and some emphasis is to be given on specific topics or a specific point that is not clear to you. Okay. That's what my request. Thank you. Yeah, so there is an interesting question by the Pojwal.
Okay. Mm. An interesting question here, yeah. Share some future directions in pure discrete event systems and areas of cyber physical systems, system security. Are there any problems intersecting optimization and discrete event system? Yeah, actually what I try to do today, I'm not sure if I will make it, but my plan is to submit a paper tomorrow morning at 9 o'clock is the deadline, where I combine discrete event system with optimization.
Okay.
And in that case, I introduce timing performance on the discrete event systems with what is called timed automata, and also some abstractions and reduction techniques to be able to solve large systems. And one of my former PhD students did quite an interesting job on that. So I think this, I mean, very much on all these aspects, at least what I am looking at is how to find more efficient algorithm to be able to solve large problems, because I mean the basic formulations are quite straight on, but the question is it possible to compute something, and for instance to optimize discrete event systems is really challenging. Then you ask about so maybe I plan to at least say some words on this on Thursday, we can say then, in my lecture then, where I also will introduce some other aspects of optimization, which actually also you asked about cyber physical systems. And I mean, what is the cyber physical system? The definition of that is absolutely not clear. And one interpretation of a cyber physical system is that it includes a mix of continuous and discrete dynamics, and continuous and discrete variables, like hybrid systems in general. Actually, I haven't mentioned about hybrid automata and timed automata yet, so I will do that also on Thursday, yes. Another aspect, which I guess you indicate here by your question, because you talk about cyber physical system security. So then the security aspects with a lot of internet communication and so on. Yeah, I mean, there are some works in our field on, for instance, different aspects of opacity, which is a notion on security, where the question is it possible for an intruder to get knowledge about some specific state when all transitions are not observable? So opacity is and anonymity is another problem, which is quite popular at the moment, and the verification of opacity, initial state, current state opacity, and so on, has been around for quite many years. But now synthesis also of systems to avoid that kind of problems has become more popular. And there is a new special issue in control system letters, that will come quite soon. I think it will be published in the end of this year or something. But if you look at opacity and cyber physical system, there are some survey papers that have recently been published where you can read more about this. And famous authors on this are yeah, if you look for Cassandra's Lafortune has done some great work there, and also Haji Costas is another person who is working in this field. So this was a way to try to answer this.
Thank you, Professor. So, shall I start recording? I forgot to start recording.
Yeah.
Thank you.
So maybe I should just quickly repeat so we get that into the recording also. On cyber-physical security, opacity is a big issue, and let's see your comment there. I have read about opacity and seen your papers with Haji Costas. Aha, okay, okay, that's good. Haji Costas is a great person in this field. And once again, synthesis is a big thing, but also optimization related to discrete event system is definitely something where we try to emphasize more on that. And there are some already an existing publication by a guy, if you take my name, Lennartsson and Hagebring, then you get a quite interesting approach to that. But I think I will come with something even better already on Thursday. So let's go on then with what I was looking at, the temporal logic. You could also say that temporal logic aspects, including involved in discrete event system, is also another, I would say, quite popular field at the moment. To mix temporal logic and discrete event systems, that's definitely something quite interesting and popular at the moment. So then I will try to illustrate some typical aspects of temporal logic specifications, and there are actually three main areas which people are talking about, or three main types of specifications. And the first one is the most important, I would say. It's a safety specification. And some people within model checking and so on, they mean that, well, okay, more or less everything is about safety. It's not much that isn't safety. So therefore, there are a number of tools that are specifically focused on safety specifications, which I think I have mentioned about that before also. This IC3, for instance, in new XMV is such a tool. And then invariant specifications are typically what is specified, or you could say that safety specifications has this always operator at the top, so to say. So always say that the temperature is in between two levels, between temperature 1 and temperature 2, that interval. Then you could ask, is the temperature always in this interval? That could be a safety specification. Another one is that, is the number of parts always in the buffer always limited to the buffer size, or is there a risk that you can get an overflow in your buffer, which of course is not desirable. You must avoid that. Mutual exclusion is another safety specification, saying that, okay, if PCK is a state label for a task K in a critical zone, so if the task 1 is in a critical zone, meaning that PC1 is true, then it's not allowed that another task is also in this critical zone. So PC1 and PC2 is not allowed, because that means that they are in the same. Say, for instance, these two robots that I introduced early as an example. Two robots that are in the common zone, that's a forbidden situation. because then they could collide with each other. So this is another type of specification, not always not PC1 and PC2. Typical safety specifications. Mutual exclusion can then be described or exemplified by two automata, where G1 has an idle free state and a critical state 1, and for the second model, critical state 1 with then labeled PC2. So this mutual exclusion specification, then we could see that, well, if you look at this synchronized system G1 and G2, we come into a situation where both PC1 and PC2 is valid in the 1-1 state. So here we have PC1 and PC2 true, and that must be avoided. How can that be done? Well, we could introduce a mutual exclusion model saying that if you go for A1 and you reach state 1 where you have the PC1, then it's not possible to execute A2 at the same time. So when A1 is executed, then A2 is blocked. And if you take this, you could say it, call that a controller, then you get instead this behavior, and there you could see that we avoid this bad state. So G1 and G2 does not satisfy always not PC1 and PC2, while when you introduce the G3, then G1 synchronized G2 synchronized G3 satisfies this, that always not PC1 and PC2. So this is a typical situation where you first have your system, you synchronize the different models, and then you test a specific property, and you find that, oh, sorry, no, our desired property is not satisfied. Then you have to do something. Either you introduce manually a supervisor, or you just, as in this case, consider this as a forbidden state. And that means that you skip these transitions to that state. And actually what you come up with then is exactly this type of model G3. And then if you synchronize that with the original model here, G1 synchronized G2, you avoid the bad state. Now we come with liveness. And liveness specifications are of this type, that something good will eventually happen. So it's rather to talk about something good that you can expect or hope for, while safety specifications are rather focused on any bad thing that never is allowed to happen. So then we could have some typical state labels around here, and you could have a request state label, for instance, an execution state label. And another notion I used here for PN is a non-marked state label. And actually here I used the notion then phi m as the non-marked, as the negation of the non-marked. That means a state label expression for a marked state. So phi m is a state label for a marked state. We will see why I introduced this negation of the marked state maybe later on here. Examples of some liveness specifications are: a marked state will eventually be reached at least one time. That is what is said here. Eventually, phi m. Always eventually specifies that a marked state will eventually be reached infinitely many times. So repeatedly repeatedly, you will reach this marked state, which is, of course, a stronger condition than the first one, where it's enough that the marked state is reached one time. And here it's interesting that especially I would say LTL specifications are, then you expect that you have infinite sequences of behaviors. So also the corresponding automata related to that, and formal languages, that they are we are talking about infinite sequences. And then instead of finite state machines, we talk about the Bicky automaton, then, which is focused on infinite strings. Another one could be that if you make a request, say for instance, a request in an initial state will eventually be executed. So if you write PR, it means that there is a request for something. Then eventually that request will be executed by the execution state label PE. Actually, the first one here, that is something where PR must be valid in the initial state, while if you put an always before, it means that you have a request at any state, that at any state you will eventually be executed. Request at any state will eventually be executed, yes. So if PR is happening in any state, then eventually you will get a PE. That is what is specified here. While the one before only says that, okay, if your request comes in the initial state, which is absolutely not necessary, I would say that the last specification is then much more relevant and normal. And here we could say that this is maybe a little bit problematic with the CTL, because here you will have this, here you get this combination of always, eventually. So just to illustrate a little bit of these liveness properties, always, eventually, phi m, and phi m means this marked state. It's true here because you can loop around, and independent of where you are, you will for sure get back into this state 1. While this model does not satisfy this expression. Why? Because here you can go around between 2 and 3 forever, actually. So that means that you will not always go back to this marked state. So that means that for this system, this always, eventually, phi m is not true, because this must be satisfied for all states and all sequences, because it's an LTL expression. So you could say that there is an implicit for all in before every LTL specification. For all sequences, you should repeatedly get phi m. Here is another situation where you also don't satisfy this phi m. You can definitely loop around here. So there exists a path where always, eventually, phi m is true, but it's not true that all sequences generate that, because from 2 you can also go to 3, and then you will never come back to the marked state. Now, if we consider 3 and 4 to be forbidden, then you can just skip these states. And then you could see that the Blindness condition is satisfied. Meaning that always eventually phi m. Another type of specification is, the third type of specification is what is called fairness. And that is specifically focused on this always eventually. While Blindness is quite often also this always eventually, but it could also be, for instance, this always PR implies that eventually you get PE. And it could also be that just eventually PE is also considered as a Blindness specification. The fairness, what is that? Well, here you see that you have two alternatives. Say that state 1 means that you use one printer and state 2 means that you use another printer. Now, if all customers go in the left direction and always use the first printer, maybe it's not so good, because then that will get problems earlier. So it's better. I mean, if you have two printers, they should all be used more or less equally, but you don't want to say exactly it should be used every second time or so. But you should at least have a fairness between using. So at least sometimes you should use this A2, this printer in the second state, in state 2. So if you have an unconditional fairness specification, it just says then that, okay, you will repeatedly go to this state where you have the critical zone PC1, and you will also repeatedly go to the other another zone where you have the critical, or when another task is using then PC2. The states with label PC1 and PC2 will both be reached infinitely many times. That is what is specified here. And if this is fulfilled, then you have fulfilled an unconditional fairness specification. Then there are some implications here that can be also included, and then it's mentioned about conditional fairness specifications. So you see that this always eventually comes quite often here when we go, especially for fairness, but also some Blindness specifications. So it's actually a very common specification. So do we have then any next and until specifications? Well, actually next is, we had some next specifications when we looked at this even and odd numbers. Yeah, I mean, there are, of course, applications where you need this next. And although some people argue that, well, actually, it's not that common that you really need that. But I think it depends a little bit on what kind of applications we are looking at. So here in this example, if we have two, so no, let's see here. We have three temperature intervals. One where the temperature is less than T1, one when the temperature is in between T1 and T2, and then above T2. So then we could say that, well, okay, the expectation is maybe that less than T1 it's too cold, higher than T2 is too warm. So being in between T1 and T2 is the desired behavior. So in that case, you could say that, yeah, you have a more or less a safety specification that you would always guarantee that you are in between T1 and T2, which was more or less what I also wrote quite early here. This was a similar type of specification. But here we could also say that it's not possible to go from state x1 to x3 in one step. Physically, meaning that to change the temperature from T1, from less than T1 to higher than T2 is not possible in one time unit. We expect that there is some dynamics, and meaning that it's not possible for this to go too quickly. On the other hand, if you are in either, or if you are in state x2 where you are in the middle temperature, then there is always a possibility that the next specification, the next state is x1 or x3. That could be expected as to something that could be true, while jumping from x1 means that the next one cannot be x3. These until specifications, they are, yeah, I mean, here is a very specific application for an elevator, which I found from the beginning was one of the few examples I could find where I had this until operator. So for instance, if you're at floor 2 and you push the button to get to floor 5 and direction up, that should mean that you should go direction up until you get floor 5. You shouldn't then change to go down, for instance, before you have reached floor 5. So this is a guarantee that if you are in the low region of the number of the floors, you shouldn't go back and forth there all the time. You must guarantee that if you have asked for button floor 5, then you should also reach that rather soon. And one specification on that is that if you have started direction up, then you must continue that until you have reached floor 5. So that's a possible specification. But this could also be illustrated by an automaton, because you could say that if you are in a state, then a transition to another state is actually an until property. Say that you have a property P in state 1 and the property Q in state Q, then you could say that you could have a specification, say P until Q. That means that if there are other options from state P, if you specify P until Q, it means that you say that, okay, the next state must be this state, this Q state. So until actually has a very close connection to automata, which why I have to say I was not, I didn't realize when I looked at this. But this is especially relevant when there is an automaton with the alternatives. We could say that that if I want to specify the opposite to this fairness, that okay, when I am in state 1, at least just now, and I want to reach 2, not state 1 at the next, not next, but because I mean there could be other things happening around the system if this is a local specification. So let's see that I call this first state there instead of having the empty state label. Say that you have a state label Q there. So then I could write Q until PC2 means that if to fulfill that specification, you are not allowed to first pass state 1. You must go in the right direction in that case. Q until PC2 means that you must go to state 2. This also indicates that actually these temporal logic expressions have a very close connection to automata. And what is done in practice is that all these temporal logic expressions, at least the LTL expressions, they are transformed to automata, and then you verify properties by synchronizing this specification automaton with the system automaton. And that also indicates that, well, actually, my main topic here on staying all the time with specifications and plant system, plant modeling with automata is not that bad. But okay, it is maybe a bit more abstract than these temporal logic expressions, as you see here. And there are situations which are better expressed by temporal logic, but there are other situations where specifications are, I would say, much easier to specify by automata instead of temporal logic. So these two techniques complement each other. Okay, so then we have 25 more minutes, or say 20 minutes. We have some questions in the end. Now I would like to introduce some aspects how to analyze this and this Mule calculus, which I mentioned before. And then in temporal logic, this is a little bit of a repetition, but then I assume that I have an automata with state labels, and actually that is also called a transition system. And if you have a system without any event labels, it's even called a Kripke structure. And here, just to show that, well, ordinary automata also have state labels, but they are on a very specific, of a very specific type, namely either a marked state or a forbidden state. But there could also be more generally other types of specifications. Let's say that I just have symbolically P, Q, and R, where P could mean that you are in a very specific safety condition or something else. Or that you are, say, on floor 5 in the building or so. In this case, we have the state label Q in state 1, Q and R in state 2, and the state label R in state 3. Now we use a specific notation here, saying that, okay, if this type of special brackets, double brackets, around a state label means that this defines the set of states including label Q. So which states include the label Q as state label? It's state 1 and 2. So this double bracket around Q is the answer to that is the set 1, 2, while R, the set of states where R is true, is state 2 and 3, because you see that in 2 you have both Q and R, and in 3 you have R. So now I will present at least the basics around a specific algorithm called Mule calculus, where I can evaluate, for instance, the existence of eventually Q, if there exists a sequence or a path where I satisfy eventually Q. And to compute the states where this temporal logic property is true is what I will show you now. And if you go for the example above here, the question was, in which states do I eventually get Q? In state 1, in state 0, I definitely have eventually Q because it's already in the next state. In state 1, I also have actually immediately Q, and also in state Q, I have immediately 2. While in state 3, I cannot get any Q at all if I go further. Actually, this is the terminal state, so I cannot do anything more, but Q is not true here. So that means that is only in state 0, 1, and 2, which it is true that there exists a path where you have eventually, finally, Q. It's only fulfilled in state 1, 2, and 0, 1, and 2. Mule calculus. That is a tool to generate algorithm for analyzing in which states a temporal logic formula is valid. This includes both LTL, CTL, and CTL star, which is actually a combination of CTL and LTL. So in CTL star, you can both write always eventually square diamond P, say, square diamond P, which you cannot do in CTL. But you can also in CTL star write, for instance, there exists a path where you eventually, where you have always eventually P, which you cannot say in LTL because the existence operator does not exist in LTL. It's always the assumption, the pre-assumption that the quantifier is always there, or not always, for all. How to then understand this Mule calculus? Well, first I would say that Mule calculus is perfect for basic CTL. And it's sometimes amazing that I have a thick book on model checking where they describe CTL with a number of algorithms, and actually these algorithms to where CTL expressions are analyzed, they can immediately and very nicely be described by Mule calculus, but it's never mentioned in the book, which surprises me because it's the standard heavy thick book, 900 pages on model checking by Bayer Katun. So for myself, I want to give the students, my students in the master course on discrete time systems, I want to give them a tool from which they can compute and analyze computationally if temporal logic expressions are satisfied. And then Mule calculus is very easy to apply for CTL expressions. It's a bit harder for general LTL expressions. But I would say that there are a set of Mule calculus formula which correspond to the most typical cases in LTL. But LTL is a bit more complicated to transform to Mule calculus generally, I would say. And why CTL is so easy? It's because of the fact that CTL always have a quantifier followed by a modality like always, eventually, until. And all these three can be rewritten as follows. And this is what is called an expansion law for this existence of eventually Q. This is equivalent to either Q is already true, or there exists a next time instance where you have that this existence of eventually Q is true. So it's a kind of recursive definition here. Existence of eventually Q is equivalent to either directly Q, or there exists a next state or a next time instance where this existence of eventually Q must be true. Now the question, how can we use this to formulate something in Mule calculus? Well, what I do here is that I see that there is something that is repeated. And then I introduce a logical variable, y, for this existence eventually Q. And then my expansion law can be expressed as y is equal Q, or there exists next y. And this expression can be iterated until a fixed point is reached in terms of if this is satisfied or not. A Mule calculus is a logic that includes specifically fixed point operators. So the syntax for Mule calculus is as follows. First, a Mule calculus formula can just include an atomic proposition. It can also include a variable. And if you have a variable or an atomic proposition as a formula, then you can take the negation of that one. You can take the conjunction of two, and there is a function for describing the next modality, including also quantifiers. So either exist next or for all next. Those are the two next operator functions that are expected here. Okay, something happened here. Okay. So far, not that very much strange things, but then comes the powerful thing here, and that is the fixed point operator. And that is expressed as mu y dot psi. And mu y dot psi is the least fixed point, while nu y dot psi is the greatest fixed point. And how to get the least or the greatest? Well, a fixed point is always an iteration, and you are all actually searching for the states where this expression, mu calculus expression, is satisfied, actually where this variable y is true, where remember that I'm searching for the states where this expression is true, where there exists eventually a q, where there exists a path such that you get eventually q. And so I'm looking for, I want to compute this, the states where this is true. And now I have introduced a variable that represents this expression. So what I'm looking for is actually the states where this y is satisfied. And if I want to start with to generate the least fixed point, then my initial value in this iteration is the empty set for this y variable. While if I'm looking for the greatest fixed point, I start my iteration with all states and go down until I get a fixed point. And there is a famous theorem around this with the smallest and the least and the greatest fixed point, formulated by a Polish logical person in the beginning of the century, last century. His name is Tarski. So given this syntax, now I would like to explain then, or give the semantics of the Mule calculus. You know, in all these type of logics and languages, you first start with the syntax, and then you come up with semantics, trying to explain exactly what happens. Now I assume that I have a given transition system, G, with a state set X, and if you are note here specifically, I use the notion here capital X instead of capital Q for the set of states. Otherwise, it's more or less the same. Capital sigma is the set of events or actions. T is the transition. I is the set of initial states. AP is set of atomic proposition, P, Q, R. And lambda is the labeling function. So given a state, the labeling function tells which atomic propositions that are true or included in this state. So lambda of 1, lambda of 0 is empty, lambda of 1 is state Q, lambda of 2 is Q, R, and lambda of 3 is the set R. Then the set of states in psi, where the Mule calculus formula holds, is defined as follows. P is a set of states where P is a member of lambda of X, where P holds in that specific state. Then the bracket of Y is the set of states where Y is true, and that is a subset of the total state space. Then if you have the negation, that is in a set. Here is the set of states where the negation of psi is true. That is the same as to look at the set, the complement of the states where psi is true. So it's capital X set minus psi. The logical operator or conjunction corresponds to, in the set operations, the intersection. And this f function I call then pre-f, and pre-f means that f means that either is then either always or there exists. So it's the quantifier that comes up there. And actually, it is a bit tricky with this pre-function. I'm sorry for that. I mean that the rest is quite standard here. And also the fixed point needs some added aspects, but I would say it's not that complicated. It's only that the notation of the set of states where mu y dot psi is true can be also expressed as mu capital Y dot capital psi of the set of states Y. And this is the least fixed point for the set of Y, where Y stands for, that's a fixed point. Y is equal to psi of Y, but it's the least fixed point. And that means that overall set of states where you have this fixed point, you take the intersection of all of them. Because remember that there are a number of states where this equation can be, where this equality can be satisfied, but the least fixed points is the one that we are looking for here, and that means that it must be satisfied for all the sets, such that this equality is satisfied. It's not enough that it's satisfied for one. And then, of course, the opposite, the greatest fixed point, then you take the union. And that means that all subsets Y where this equality is fixed point is satisfied are summed up together, and that generates the greatest fixed point. And that was what I tried to say here. So before we take a break, and I will exemplify this algorithm this evening for you, I will just try to define what I mean by this pre-function. Sorry. To understand the pre-function, I introduce first the transition function in the automaton, and I also include this active event set, meaning that if I have a given state, I'm looking for which events are possible in that state X. So possible events defined in state X. So for instance, in state X, it's possible to generate event A and B. So that means that sigma of X is equal A comma B. Now, pre-existence of Y corresponds to the existence of next Y. That means that we are looking for all X such that there exists an event A in the set of active event set such that delta of X is a subset of Y, of the current state set. So if you go one step for a backward, so to say, the pre of state set Y means that you're looking for states from which you can make a transition to a state that is a member of Y. this will be clear when we go for the examples, but I mention at least this specifically here now. For at least one event A, x prime equal to delta of x comma A is a member of Y. Is the same as to make a co-reachability one step backward. So actually, this pre-existence of a set is just that you go backward one step for all the events in all the states you have in this Y function. So actually, this is not that difficult to execute. For all, then it's a bit more critical because then the demand is higher, namely that this delta of x comma A being a subset of Y must be satisfied for all active events in sigma of x. So that means that all target states from x must belong to Y, which is a very important distinction compared to the existent. Because there it's enough that at least for one event A, the next state is a member of Y. But here, all target states from X via all possible events must belong to Y. Okay, so I think I take this example before I take the break, just to give you some feeling of what we're talking about, and then I will give you a number of more examples this afternoon, or sorry, this evening for you. So here I have initial state, and then I'm looking for the states where I have the label P and the pre-existence of that. So the pre-existence of the state where P is satisfied, that means that I go for state 2 and go one step backward. So pre-existence of 2 includes going backward from 2, includes 1, but also go back to itself. So that includes also 2. That was with the existence. With for all, that means that state 0 is not included, since state 1 is missing in the state set 2, which I'm starting from. So the meaning of this is that pre for all, then if I go one step backward and look at this state, are all the events going to a state where this P is true? And that's for sure not true, because in this state, I can also go to a state where P is not true. It's not involved. While if I go in state 2 and go backward to itself, then P is a member of that. So that means that pre of P, then you only include those states where you satisfy this, that from 2 it's possible to get to also state 2, and you started with Y equal 2. This for all, it's a bit tough to understand. I fully understand that, and that has also been a trouble for my students. But I will take some more examples on this after the break. But now I think it's enough for this time. So this afternoon we will take a somewhat shorter presentation, but if there is any specific question now, I'm happy to answer that.
Thank you, Professor. Participants, any questions? Please put your videos on so that we can take your pics also. Thank you. Thank you. I request Shubhangi to please take the snapshot. Shubhangi, are you there? Thank you, Professor. Thank you, all of you. Any questions you have?
Okay, doesn't look like that. So then we come back. How is it now? Is it in 3/4 or I don't remember?
So there is no, as we discussed in the revised schedule, today there's no further tutorial.
Oh, okay. Oh, okay. We skipped that today. I'm very thankful for that. I'm very thankful for that.
Yeah, because you have,
because then I get some more time for my paper
submission.
Great. Thank you. Okay. And tomorrow you give also the lecture.
Tomorrow is my lecture, yeah.
Yeah, and then I will come back on Thursday, and then
Thursday
I will give you much more examples.
Yeah.
On this issue, and then I will also come back to this time optimization, which I think could be quite interesting.
Yeah.
To